about 6 seconds. Now I'm going to turn on the power again. Okay, so the PC operating where it can crash. So basically, this system is crash-proof. So the magic in this system is NVDIMM, and I'm going to take you to it, how we did this. Okay, for those of you who are not familiar with NVDIMM, let's do a brief review of NVDIMM module. NVDIMM is a non-volatile, it's a hybrid non-volatile memory technology. It is consistent of ordinary DRAM, flash, ultra-capacitor, isolation mux, and controller. So during the normal operation, it operates just like ordinary DRAM. When a power loss event occurs, with the help of ultra-capacitor, in a brief moment, data is saved from flash to DRAM. And after the power is restored, data can be restored from DRAM from flash to DRAM. So NVDIMM is a bridging technology towards the next generation storage class memory. Storage class memory is a memory that you can use to replace main memory and persistent storage, like hard disk drives. To qualify for storage class memory, you have to qualify 4 conditions. The first, it has to be fast, random access speed like DRAM. Second, it needs to be non-volatile. The third, it has to be a solid-state device. And the fourth, it needs to be cost-effective. So some of the leading technology candidates for the SCM storage class memory are RAM, STT-RAM, and PCM. I think some of you might not agree with me, but it's safe to say today those technologies are not commercially mature yet. And as for NVDIMM, it naturally qualifies the 3 conditions of SCM because it has DRAM speed, it's non-volatile, and it is solid state by nature. As of the fourth, the cost effectiveness, because of the availability of flash and basically the technological maturity of flash, today it is the cost-effective solution. So as of today, NVDIMM qualify all 4 conditions for SCM. So today, at this point, NVDIMM can be qualified as a storage class memory. NVDIMM can be used to build a persistent system. There's 2 types of persistent system. One type is partial persistence, where you have a mixture of volatile and non-volatile memory. And for that, it's block-based that you need a non-volatile heap structure, and it requires state conversions between them. And it's very difficult to transform and maintain legacy programs because sometimes you don't even have the source code of these programs. The other type is whole system persistence, where all states are retained in non-volatile memory. Basically, it can be achieved by flush and fail, where you have the power loss event occurs. So individual program doesn't need to save all the states. The states are saved automatically when the system are powered down. So it's very good for program backward compatibility. So in order to use NVDIMM to build a WSP, it requires NVDIMM, of course, and then power monitor supply and a little bit of software control. And for the convenience of the system, we can use flush and fail, which are already existing in today's computer system, which is ACPI S3 state. Next, we will go through the WSP functional flow. So during the data backup path in the normal, when a power down event or a power loss event occurs, first you wake up the NVDIMM, wait for the suspension, for system enter suspension. So system is going to flush all the states and save all threads and save them to the flush them to the memory, and then we can back up, use NVDIMM to back up to a flash. And then NVDIMM saves the power down event marker in the flash. Then you're done. The next time when you restore the operation, so first the device is going to determine whether last breakdown or power down is normal power down or due to a power loss event. So during the pre-boot process, you have a choice to enter normal boot or enter a boot we see similarly. So if you want to boot from where you left off, so you enter the S3 state and then restore the data from flash to DRAM, and then you wake up the system, like what we've seen before in this system. With that, we go into the product design goal. So we want to build a non-volatile system with all state retainable, and it should be compatible with the existing computer architecture. We don't want to modify quite a bit of the existing computer architecture, and want to be backfitted to support off-the-shelf computer system if we can. And we also want to have a cost-effective system upgrade. We don't want to modify a lot of system, operating system or your programs. So there's a few challenges to do that, and let's go over through them. So first of all, you want to save data in time, okay, during the power loss transition. There's two factors. One is the energy ultra capacitor provided during the data backup. The second is bandwidth of the data transport during the save routine. Actually, those two are related. The higher of the bandwidth of data transportation, the shorter time requires for data to be backed up, the less energy requires for the capacitor, and smaller size for the ultra capacitor. The second is software support. Ideally, you want to have BIOS support, but if you don't, there's a solution around it. So we will go next. You can use device firmware to do what we did here. Okay, this is exactly what we did in this system. The third is compatibility with the existing computer. Ideally, we want to have a computer which is plug and play. You just plug in the NVDIMM, and then you have a WSP system. The other one is the placement ultra capacitor. Let's face it, that today's computer architecture of chassis design is just not fit for the so many ultra capacitors to be in the chassis, because it blocks the airflow and creates all kinds of thermal problems for it. Okay, next. So with that in mind, I propose that we have a centralized backup power supply. Basically, you move all the ultra capacitor outside of the computer chassis, computer system. It should have three functions: power monitoring circuitry, provide the power warnings to the system, and then you have ultra capacitor to provide the emergency power supply. So this is actually basically an ultra capacitor based UPS. You use that to replace the battery based UPS. This is you use one stone to kill two birds. First, you replace the battery, which is costly to maintain and environmentally not green, and among other defects. Second, you remove the headache where you put the ultra capacitor in the computer chassis. The other thing we did is we used the adapter-based NVDIMM design. So we have an adapter which will transform what you have in a normal DIMM to an NVDIMM. It can transfer a 4G, 8G, or 16G. The problem here is this is a double-edged sword solution. The good thing is you have flexibility to transform 4G, 8G, or you like. Basically, our controller will transform that. The bad thing is go through the adapters that you have to lower your DRAM speed. So this is a double-edged sword. So this is a problem we're still working on the board. The core of our technology is the controller design. To measure the performance to measure performance of controller, what we want is we want to have the highest bandwidth during the data transition time. To achieve that, you want to have massive parallelism to utilize what you can have for flash. So basically, we build a very scalable design. We can just add flash channels into the design. And also we put a PCIe interface into our controller. And it helps us in the device, in the device firmware. Basically, we bypass the BIOS. Okay. Yeah, so this is the core technology of our design. With that, we built a two prototype system. The first is Wugo 2E. It has 8 channels and DDR2. It achieved the program speed of 125 megabytes per second, and you can restore them in 266 megabytes per second. The second prototype we did is the Wugo 3, which is 16 channel DDR3 controller. The program speed is 350 megabytes and restore speed is 590 megabytes per second. The whole system persistence can be achieved with little changes to existing hardware. The centralized audio capacitor is good for WSP control. Multiple channels can increase your bandwidth, reduce the size of audio capacitor requirements. The last is NVDIMM is the bridging technology towards next generation SCM.